Lecture, we'll be discussing the synthesis of acetylsalicylic acid, more commonly known as aspirin, right? And you can see here the molecule. So to start off, I'll be going over some of these analgesics, right? So aspirin is considered an analgesic, right? Meaning it's used as a pain reliever. You can see here aspirin has antipyretic properties, meaning that it reduces fever. It is also an anti-inflammatory, analgesic, of course, and it is a blood thinner. And this is the structure for aspirin, or acetylsalicylic acid. Acetaminophen is an antipyretic as well. It does not have anti-inflammatory properties though. And of course, it's an analgesic. And you can see here acetaminophen. You have the amide here instead of the acetyl group with the oxygen. And you also have an OH here on the para position as opposed to a carboxyl group on the ortho position. Ibuprofen is an antipyretic as well. It's anti-inflammatory and analgesic, but it's not a blood thinner, unlike aspirin. And you can see here's the structure of ibuprofen. You'll notice here there's a chiral center. It turns out that if you go to the store and you buy the cheap ibuprofen, if I'm not mistaken, it actually comes as a racemic mixture, which is why it's cheaper to buy it at the store. So then you have here finally naproxen, which is antipyretic and anti-inflammatory. And this is the structure, right? Also another chiral center. This is, I believe, in the stores it is Aleve. This is Advil. This is Tylenol. And I'm not sure which brand is aspirin, but these are basically all the painkillers you can find at the Walmart or wherever you go. So this synthesis is actually not that complicated. You start off with an anhydride here. You'll notice anhydride is anhydro, right? So that means that there's no water. And so it's very important to know that this is very extremely reactive to water. And you'll remember that we are composed a lot of water. So this is dangerous for us too, okay? So that's important to keep in mind. But the reaction starts off with protonation of this carbonyl with phosphoric acid here. So you have here your carbonyl, which is protonated, and it has this carbon here that it's easily able to have a nucleophilic attack. It's electrophilic. So the alcohol from this salicylic acid is able to easily attack this carbon right here to form this hydroxyl group here. Okay. The next step is the removal of this hydrogen from the salicylic acid, and so you end up with this oxygen here on its own here, as you can see right there. So then the next step is a protonation of this other carbonyl on the anhydride, and then this hydroxyl group on the original reaction center where the carbonyl was, it attacks back to form a carbonyl, and it releases this substrate here, right, to form this byproduct, which is acetic acid or vinegar. And you have also your final product of the acetylsalicylic acid, or your aspirin. So here is the procedure, right? So here are the different things you will need for this reaction. Of course, you need a very clean and very, very dry flask, because that anhydride is very reactive with water. You need 1.4 grams of salicylic acid. You need 3 milliliters of acetic anhydride, right? Because it's a liquid. And wash it down with any product that might be stuck on the sides of the flask, right? And you need only 5 drops of phosphoric acid. In this case, the phosphoric acid is a catalyst because at the end of the reaction, you end up with acid, right? So the first step is to place your 1.4 grams, which is 0.01 moles of salicylic acid, into your Erlenmeyer flask. You then add your 3 milliliters of acetic anhydride. You can weigh this, right? It's 3.1 grams, but you have to weigh it in the Erlenmeyer flask, which is 3 equivalents of this starting material. And then you have to do it in such a way to make sure that none of the material gets stuck on the sides, right? You then add your catalyst, the phosphoric acid, 5 drops. and then you heat between 85 and 95 degrees Celsius for 5 minutes on a hot plate. Of course, when you're heating, you always have to be very careful. Please clamp everything, because otherwise you could injure yourself. Now, when you're heating your reaction, you could place it directly on a hot plate, but there's another method you could use to have better control of the temperature. You can use a hot water bath, right? And you just place your flask into the hot water bath and let it boil in there. Of course, it has to be clamped, right? And as well, you have to monitor the temperature of the reaction, right? Because it needs to stay around this temperature. You could either place the thermometer in here or even directly inside of the flask. And this is only just to make sure that you have the right temperature, because sometimes placing things directly on a hot plate can cause them to become too hot. So that's the reason. So the next step is in order to neutralize any excess anhydride that may have not reacted. So you have to be very careful with this step, because the anhydride is extremely reactive with water, right? So it will most definitely probably vigorously bubble. So you have to be careful with that. Then you remove the flask, and without allowing it to cool, add 2 milliliters of water in one portion. Of course, as I said, be very careful here. The temperature shouldn't be too high. You should make sure that it is at 85 to 90 degrees. If the reaction is boiling, allow it to cool to this temperature, right? So the excess acetic anhydride will decompose vigorously, and the contents of the flask will come to a boil, right, as soon as you add the water. So once your anhydride has been neutralized, you will have to add more water, right? So add 20 milliliters of water and let the flask stand at room temperature until crystals start to begin forming. Now this is a tricky step. Crystallization is, it can be tricky. It sometimes doesn't happen. If you see that there aren't any crystals, you could scratch the sides of the glass, right? And this could create seed crystals in the glass and allow the crystals of the product to start forming. So basically the crystallization happens when the product becomes insoluble and it starts to get together into regular crystal structures, right? As we discussed in a previous lecture. Once you start to see crystals forming, you should place the flask into an ice bath. This will allow more crystals to start to form. You can add 10 to 15 milliliters of cold water in order to help with the formation of crystals. The cold water is because it's less soluble, right, if it's in cold water versus water that you just boiled. So it'll probably not be that hot anymore, but adding cold water will help speed the process up of forming these crystals. So basically just wait until all the crystals are formed, and yeah. Then it's time to collect your product. So you would use this setup as we've seen before. Of course, as always, please remember this needs to be clamped. The Buchner funnel goes on top with a correctly fitting adapter to the flask, and then you just pour your product through with a filter paper, of course, and you'll end up collecting your crystals up here. Make sure that you completely dry them, right? And then you take their weight and calculate their percent yield of recovery of the reaction. If you want to make sure this is completely dry, you can press down on it with a spatula or something to make sure all the water is gone. It's difficult to dry these things in the class when everything is in a hurry, but for the most part, you should have less than what you started off with, not more, right? Because usually what ends up happening is there's too much water, and people end up getting a higher mass than what they initially expected. So that's one thing to look out for with this part of the procedure. And as I mentioned earlier, this is a very dangerous reagent, the acetic anhydride. Remember, we're made of water. Well, not completely, but we have a lot of water in our bodies, and it's very reactive towards us. There's also other compounds in our bodies that react with it. So you want to be very careful not to inhale it. It can also injure your eyes pretty severely. It can cause serious chemical burns on the skin. So if you ever get any of it on your skin, if you were to do this procedure, you'd make sure you have to wash very thoroughly with lots and lots of water. And you would alert me or your instructor. Remember that this reagent reacts vigorously and sometimes even violently with water, so be very careful when using it. And when it's hot, it's a lot more reactive, right? So be careful with that as well. So when handling these reactions, make sure the opening of the flask is always pointed away from you. You don't want to be looking into your flask. That's very dangerous to do. So next, it's time to do your weighing, right? As I mentioned earlier, make sure that the crystals are very dry when you're weighing them. You then have to weigh them, right? So the next step is you take the melting point to see if you actually got your product, right? The melting point is between 140 and 142 degrees Celsius. And we will cover this later in the semester, but there's also these machines called IR and NMR, which are characterization techniques, and you can use them to determine if you have the product or not. So this is infrared and this is nuclear magnetic resonance imaging, right? And then you determine your percent yield from the weight. And this concludes this lecture. Please don't hesitate to email me if you have any questions. Of course, we're not in class because of the pandemic, but please feel free to stay in contact with me if you have any doubts or whatever. All right, and thanks for listening.